All right, so if we want to use the tangent line to f of x equals e to the x at x equals 0 to approximate f of 0.1, then what we have to do is we first need to write the equation of the tangent line to f of x equals e to the x at x equals 0. Please, and y'all are getting so good about this, but please make sure you show all your steps. The two things that you need in order to write the equation of a tangent line are the slope at the specific point and a point. So we have to take the derivative, find the derivative at x equals 0, and find the corresponding y value of f when x is 0. So the equation of my tangent line is y minus 1 equals 1 times x minus 0. And since I'm using it to approximate a y value, I went ahead and solved for y. So the equation of the tangent line equals y equals x plus 1. So f of 0.1 is approximately the same thing as y of 0.1, which is 1.1. And the reason that I can use the tangent line to approximate f of 0.1 is because my tangent line touches that graph at x equals 0, which is really, really close to 0.1. Now, would I want to use this tangent line to approximate f of 1.1? No. I would probably want to write the equation of a tangent line that's tangent to e to the x at x equals 1. So to use your tangent line for an approximation, the x value needs to be very close to that point of tangency. All right, so this is a reasonably good approximation. However, as we move away from the point 0, or away from the point 0, 1, the graphs move further away from each other, and the accuracy of the approximation would decrease. So if I wanted to approximate, say, f of 0.2 or f of 0.3 or f of 0.5, then the actual graph and the tangent line are not as similar at those points. To improve on that the approximation, you can impose another requirement, and that is that the values of the second derivatives of p, which we're going to call p the polynomial approximation. So in this case, the tangent line is my polynomial approximation, and f is the original function. So we want for the second derivative to agree when x equals 0. All right, now, the way that we do that, and we can now even make subsequent derivatives agree at those points. The way we're going to do that is through a Taylor or a Maclaurin polynomial. And it's a formula that looks really, really scary, but is pretty darn simple to use. First off, if a Taylor polynomial is the general one, and it's kind of like writing the equation of a tangent line at a specific point, except it's not going to be a line. It's going to be a graph that looks more like the original graph. It's got curves in it. If c equals 0, so if the x value that you're trying to find the approximation is close to 0, it has a special name and is called a Maclaurin polynomial. But the bottom line is that let's say that I wanted to find the third polynomial, then I would find at, say, x equals c, and I'm going to be given f of x. So I would find f of c, and then plus f prime of c times x minus c, plus the second derivative at x equals c over 2 factorial times x minus c squared, plus, and then I would go on to the third derivative at x equals c over 3 factorial times x minus c cubed. So there's definitely a pattern going on there with all of your numbers. If c equals 0, then instead of x minus a number on all of these parts up here, it's just going to be x minus 0 or just x. So the Maclaurin polynomial is nicer. It's a little bit easier to deal with. As n increases, which n is the number of terms you're going to have, then the graph of p becomes a better and better approximation of the graph of f of x. Okay, so let's just jump into this and do this for f of x equals e to the x. So we're still kind of working with the same function. So find the 4th degree Maclaurin polynomial. So that means that the fact that we're using a Maclaurin polynomial means we're going to use that c is 0 and use it to approximate f of 0.1. All right, the way I do this is if I'm going to use the 4th degree Maclaurin polynomial, then that means that I need to go to the 4th derivative. Because notice that the derivative number matches the exponent for each term. Like when we're using the second derivative, we're going to have x squared. And when we're using the third derivative, we're going to use x cubed. So if I'm using the fourth degree, I'm going to have to take my derivatives all the way down to the fourth derivative. Well, we're starting with an easy one. So f of x is e to the x. F prime of x is what? E to the x. F double prime of x is e to the x. The third derivative is still e to the x. And the fourth derivative, once you get past usually the third derivative, you can just put the number up there. So f4 of x is e to the x. Now my formula says I'm going to need to evaluate all of these derivatives at x equals what? Not yet. For the Maclaurin polynomial, we evaluate the derivatives at 0. Okay? Once we get my polynomial, then I'm going to plug in a 0.1 for x. All right, so, and guys, this is, I know that e to the x is the same thing all the way down, but I think it's good to get in good habits of organizing your work here. So I need to find f of 0, which is 1. F prime of 0 is 1. F double prime of 0 is 1. F triple prime of 0 is still 1. And the fourth derivative at 0 also equals 1. So those are the two, that's what I need, all of the derivatives at x equals 0, what I need to plug into my formula up here. All right, so if I'm writing the fourth degree polynomial, I'm going to call it P4 of x. And P4 of x is going to equal f of 0, which was what? 1, plus f prime of 0, which is 1, times x, so just plus x, plus the second derivative at 0 times x squared over 2 factorial. So 1x squared over 2 factorial, plus the third derivative at 0, which is 1 times x cubed over 3 factorial. And what will the fourth term be? 1x to the fourth over 4 factorial. And notice that your factorials also match the power of the exponent of x and the derivative number. Okay, so find the fourth degree Maclaurin polynomial for f of x equals e to the x. That's what I've done right here. Now I'm going to use this polynomial to approximate f of 0.1. So f of 0.1 is approximately P4 of 0.1, which would be 1 plus 0.1 plus 0.1 squared over 2 factorial, which is just 2, plus 0.1 cubed over 3 factorial, which is 6, plus 0.1 to the fourth over 4 factorial, which is 24. And to save us time, I am going to tell you that that approximation is 1.105 1708. Now, you're only required to go to 3 decimal places, but on this section, I tend to put a lot of decimals out. I don't know why. All right, so we used the tangent line to approximate f of 0.1, and then we used the fourth degree Taylor polynomial, and every Maclaurin polynomial is a Taylor polynomial, but a Taylor polynomial is only a Maclaurin if that c is 0. It's kind of like the square is a rectangle, but a rectangle is not always a square thing. So if I say Taylor polynomial, then c could be any number, including 0. But if I say Maclaurin polynomial, we're restricted to c being 0. Okay, so up above, we use the tangent line to approximate f of 0.1, and I've alluded to the fact that this Taylor polynomial is going to be a more accurate approximation. So if I go to my calculator Do you think that e to the 0.1 is going to be closer to 1.1 or 1.1051708? Yeah, the second one down here. And if you don't have your calculator handy, that's no big deal. I'll do it for you just to prove it to you. Right. So e to the 0.1 is that. And that's pretty darn close to what we got with our fourth degree Taylor polynomial. Okay, the question is, why are we finding this approximation when we can just type in e to the 0.1 and figure out what it is? Because this is how your calculator is programmed to find e to the 0.1. Basically, you're learning how the calculator is doing this. Yes, so your human calculators. Yeah. Basically, your calculator is programmed to do an infinite Taylor polynomial to get the approximation. It is a lot of work. Calculators are amazing machines. Well, it's a computer program. But like when your parents were in high school, well, yeah, they were called tables, and they probably ask your parents about trig tables, and they'll remember it. Instead of finding like the sine of 32 degrees, which is not off of a special right triangle, instead of using a calculator, those weren't invented yet, and so they had this table of the sine, cosine, and tangent of all of the angles. And somebody cranked out all of those things by hand using Taylor polynomials to come up with those. Yeah. So, I mean, in reality, are you ever going to have to do this in your lifetime without the calculator? No, but some of you might go on to program calculators, and so now you kind of know what's going on. Another thing I want to show you is, and I'm so prepared today, I have e to the x in y1, so the original function, and then I have this Taylor polynomial that we created in y2. And if I graph this, it's going to graph e to the x first. So there's my e to the x. And there's my Taylor polynomial. So it's kind of a parabola type shape kind of thing. And you can see if I were to zoom in some, that the values, the two graphs around x equals 0 stay closer to each other longer than the tangent line stayed close to e to the x. Does that make sense? Okay. So the higher the Taylor degree polynomial, the better your approximation is going to be. Kind of cool. And it's not really, I mean, as far as this concept, writing the Taylor polynomial, that's as hard as it gets. Now, we could use a little bit more complicated function than e to the x, but it's not too difficult.
Okay, so let's let f of x equal sine x, and we're going to find the fifth degree Taylor polynomial centered at x equals 0 for f of x equals sine x. All right, so the fact that it's a fifth degree tells me that the first thing I'm going to need to do is I'm going to need to take the derivatives all the way down to the fifth derivative. And I'm going to start by rewriting my problem just that f of x equals sine x. So f prime will equal cosine x. F double prime will equal negative sine x. The third derivative will equal negative cosine x. The fourth derivative is sine x. And the fifth derivative equals cosine x. And then I need to evaluate all of those derivatives where the Taylor series is going to be centered. So in this case, at x equals 0. So I need to find f of 0. The sine of 0 is 0. I need to find f prime of 0. Cosine of 0 is 1. F double prime of 0 is 0. The third derivative at x equals 0 is going to equal -1. The fourth derivative is going to equal 0. And the fifth derivative will equal 1. And you can see that there's a pattern going on here. All right, so now I am ready to create my Taylor polynomial. So I'm going to label this as p sub 5 of x. And that's not necessary, but I just think it's a nice visual to the fact that you've used the fifth degree to make this approximation. All right, so going back to your formula, you start with f of 0, which in this case it's 0, so I don't have to write that. And then the next step is the first derivative times x to the first power. And then technically it would be the second derivative times x squared over 2 factorial, but that term is going to be 0. And then my third derivative is -1, and that's going to be times x cubed over 3 factorial. And technically next, plus 0 times x to the fourth over 4 factorial. And then plus the fifth derivative, which is 1 times x to the fifth over 5 factorial. So we have created the fifth degree Taylor polynomial for f of x equals sine x. All right, now we're going to use that to find an approximation for sine x at a specific x value. So part B says find p sub 5 of 1.2. What that notation means is use that fifth degree Taylor polynomial that we just created and plug in a 1.2 for x. So p sub 5 of 1.2 literally means you're going to go up here to this equation right here that you just created, and everywhere you see an x, you're going to plug in a 1.2. Obviously, you would want to do this with a calculator. Back in the olden days, before calculators, they cranked this out by hand. But if you type that into your calculator, you get 0.932736. And then I'm asking, what is the value of f of 1.2? So this you for sure have to have a calculator for. F of 1.2 is literally finding the sine of 1.2. So in your calculator, you would type in the sine of 1.2, and that value is 0.932039. And the whole point of this Taylor polynomial was that before they had calculators, they would use the Taylor polynomial to make these approximations for the sine of 1.2. But I'm just kind of getting you used to all of this and showing you that it really is a pretty good approximation. And then also talk about the error of our approximation. Well, the error of our approximation is symbolized by f of 1.2 minus p5 of 1.2. Your error is the difference between the actual value, and we've talked about this in terms of alternating series, and your approximation. So f of 1.2 is the actual value, p5 of 1.2 is your approximation. And error is always a positive number, so you take the absolute value of it. So the error of this approximation is taking that actual value, 0.932039, and subtracting the approximation, which is 0.932736. And I'll go ahead and write the absolute values there. And that is 0.0006969. And once again, this is just to kind of make a point here. Tomorrow, we're going to kind of go back in time and pretend like we don't have the calculator, and therefore we wouldn't have been able to find this actual value right here. And I'm going to teach you how to find an error bound on these approximations, just like we did with alternating series. Okay, so we're just going to do this all again, except we're going to use a different function to approximate with the Taylor polynomial. Taylor polynomials are something that are very heavily tested on the AP exam, and once you do this a few times, you will be able to knock it out very, very quickly and be thrilled every time they want you to do it because it will be so easy. Okay, so for number 4, we're going to find the Taylor polynomial of degree 4. So that means I've got to go all the way down to my 4th derivative. So f of x is the natural log of x. F prime of x then is 1 over x, which I also know is the same thing as x to the negative 1. And the only reason I'm writing that is that I need to continue to take derivatives here. So f double prime is negative x to the negative 2. F triple prime, or the 3rd derivative, would be 2x to the negative 3. And my 4th derivative is negative 6x to the negative 4. And then remember, your next step is to evaluate all of these derivatives where your function, where your Taylor polynomial is centered. So in this case, it's at c equals 1. So this is the first time we've seen a centering point other than x equals 0. So I need to find f of 1. The natural log of 1 is 0. I need to find f prime of 1, which is just going to be 1. F double prime of 1 is negative 1 to the negative 2, so negative 1. The 3rd derivative at x equals 1 is 2. And the 4th derivative at x equals 1 is negative 6. And now I'm ready to just use that formula to write my 4th degree Taylor polynomial. So this time I'm going to call it p sub 4 of x. All right, my first term is always f of that c value. So in this case, it's 1, which in this case is 0, so I don't need to write it. So my next term is the first derivative times x minus c. So remember, c is now something other than 0, so I'm going to have x minus 1, and then to the first power. Then I take my second derivative, which is negative 1, times x minus 1 squared, divided by 2 factorial. And then my third derivative, which is 2, times x minus 1 to the third power over 3 factorial. And then my fourth derivative, which is negative 6, times x minus 1 to the fourth power over 4 factorial. And for our purposes, I'm perfectly happy for you to leave your answer just like that. There's no need to simplify these values like 2 over 3 factorial just for the sake of simplifying it, but you're welcome to. On this particular example, I'm going to go ahead and simplify it because I'm going to come back to it in just a minute to show you something. So if we do simplify those coefficients, then our Taylor polynomial becomes x minus 1 minus x minus 1 squared over 2, because 2 factorial is just 2. And then 2 over 3 factorial. 3 factorial is 6, so 2 over 6 just reduces to 1/3. So that will be x minus 1 cubed over 3. And then 4 factorial is 24. So 6 over 24 is 1/4. So I just have x minus 1 to the 4th on top, and then divided by plain old 4 once I reduce. And we'll come back to that in just a second. If this was a multiple choice question, then your answer choices would be listed in the simplified form. But on a free response question, it is perfectly acceptable to leave it in this first part like we did up here. Okay, number 5 is actually even easier than what we've been doing, because if you'll read this, it tells us the values of g of 2, g prime of 2, g double prime of 2, and g triple prime of 2, and we want to write the Taylor polynomial of degree 3 for g centered at x equal 2. So essentially what they've done is they've done all of this work that we had to do up here, where we had to take the derivatives and evaluate the derivatives at that c value. So that's already been done for us. So all we have to do is plug this into the formula. So I'm writing a third degree Taylor polynomial. I'm going to call it p sub 3 of x, and just start plugging into that formula. So we start with g of 2, which is 3. Then we take the first derivative, which is negative 4, times x minus 2, because we're centered at 2, to the first power. Then I need to take the second derivative, which is 7, times x minus 2 squared over 2 factorial. And then the third derivative, which is negative 5, times x minus 2 cubed over 3 factorial. And again, for a problem like this, you are more than welcome to just leave that answer just like that. Okay, last problem. And this is a little bit different, but this is something that they like to ask as well. It's just kind of a spin-off of what we've been doing. And it's actually kind of going backwards from what we've been doing. We've been creating the Taylor polynomial. Now, the Taylor polynomial has already been created for us, and we're supposed to kind of break it apart and go backwards. Okay, before we get into that though, I just want to remind you that each term of your Taylor polynomial, remember, is made up of the nth derivative at your centering point, and I'm going to use 0 because this one is centered at x equals 0, times x to the n power all over n factorial. So a couple of things that I want to remind you of and point out is that the derivative number, the exponent, and the factorial all always match, at least at the very beginning, like when you're creating the Taylor polynomial. Now, when you go back and simplify those terms sometimes, then they're not going to match. But at the beginning, when you're creating that Taylor polynomial, the derivative, the exponent, and the factorial are all going to match together. All right, this part of the formula right here is called the Taylor coefficient, because it is the coefficient of each term in the Taylor series. A coefficient is the number that's in front of your x. So the nth derivative over n factorial is what creates the coefficient in front of your x in each term. So for example, on the x to the 5th term here, the coefficient is 1/5. But what that means is that 1/5 was made up of the nth derivative over n factorial. And this is where we're going to go back to that last example. So in this form right here, this first form where I didn't simplify on number 4, you can see that I've got my second degree right here. The exponent is 2. Then that means that this negative 1 was my second derivative divided by 2 factorial. I go to the degree of 3, the power of 3, and I have my third derivative over 3 factorial. But then when I simplify it, it just becomes a coefficient that has just kind of all melded together. So what we're going to have to do is we're going to have to go from the simplified version back to the unsimplified version in order to specifically identify what the specific derivatives are. So if that's not making sense, hang on just a second, and I promise that it will. Okay, so let's jump into this. So I want to find f of 0 first. All right, well, the formula for my Taylor polynomial says that I always start with that f of 0, and that's the constant term. Well, for this particular Taylor polynomial, there is no constant term. So f of 0 has to be 0. Let's go back to this formula for finding every single term of the Taylor polynomial. So we know that the derivative number has to match the exponent. So if I'm trying to find the second derivative, it's got to be attached to the x squared term. Well, there is no x squared term up here. I only have odd powers for my exponents, odd numbers for my exponents. So f double prime of 0 is also equal to 0. And that's because there's no x squared term. All right, the third derivative. We're actually going to do something here. All right, so my third derivative has to be attached to the x to the third term. But that whole term is made up of the third derivative times x to the third over 3 factorial. So I'm going to go up here to my third degree term, and that third degree term is negative x to the third over 3. But you have to remember that that's made up of the nth derivative at x equals 0 times x to the third over 3 factorial. So I can basically knock off these x cubes because I have an x cubed on either side of the equal sign, and what I'm really looking for is, oh, I should have said this is the third derivative. What I'm really looking for here is this third derivative. So I just have an equation here that I need to solve. I essentially have negative 1/3 is equal to the third derivative divided by 3 factorial. And if I cross multiply, then I get that the third derivative is equal to negative 3 factorial over 3. And that's 6 over 3, so we could reduce it to negative 2. So my third derivative is equal to negative 2. All right, let's try it again. The next one is the ninth derivative, f9 of 0. That's the ninth derivative at x equals 0. Now, this takes it even a little bit step further because I know that that's going to be attached to the x to the ninth term, but I don't have an x to the ninth term because it just kind of quit writing those out for me. So I'm just going to continue to follow this pattern. My next term is going to be x to the 7th over 7. And it's going to be negative. Notice that I have only odd exponents and my signs are alternating between each one. So then it's a 7. And then the next term is going to be plus x to the 9th over 9. So if I want to find that ninth derivative, the way I'm going to go about that, and I'm going to kind of skip a little bit of a step that I did the last time. I know that that ninth derivative is going to be attached to the x to the ninth term, and I know that the ninth derivative over n factorial makes up the coefficient. So I'm just going to look at the coefficient of this term. So x to the 9 over 9, that coefficient is just 1/9. And I know that that has to be made up of the ninth derivative over 9 factorial. And the only thing that I'm skipping here is just writing in the x to the 9th. And there's no need to do that because there's an x to the 9th in this term, and then the x to the 9th in that whole formula for that whole term right there. But if it makes you feel better to write it in, then by all means. All right, so I'm really just trying to solve this blue equation right here. So if I cross multiply, then I get that the ninth derivative at x equals 0 is equal to 9 factorial over 9. And that's a perfectly acceptable answer, but remember that 9 factorial means 9 times 8 factorial, and then your 9s will cancel. So your ninth derivative is 8 factorial. So all we're doing here is taking a simplified Taylor polynomial and trying to go backwards and extrapolate the two numbers that reduce to make that coefficient. So this 1/5, that is the coefficient in front of x to the 5th, was made up of the 5th derivative over 5 factorial.